Okay, good morning. Uh, Please turn on your computer screens and let's get ready to start the lecture for today. Um, so I brought the exam grade with me today. I'll pass the exams by the end of the class lecture, and we'll probably discuss some of the problems. If you have a specific questions, we'll go over them. But not going to spend a lot of time in class discussing the exam. If you have extra questions, you can go to my office and we can discuss them. So for today, what we're going to do is we're going to continue explaining other methods. We already know to solve LP problems. We already know how to solve problems using the graphical method and the simplex algorithm. But what happened is that with the simplex algorithm, there are some cases that you cannot apply the algorithm straightforward. You can see that there are some cases in which you have to do some modifications to the problem and also some modifications to the algorithm in order to get a solution. So those are the cases that we're going to be discussing today. So the title for the lecture is Artificial Starting Solution, and this is also part of your chapter 3 in your textbook, the Simplex Method and sensitivity analysis. This part we're going to start covering next week. So next week we'll probably talk about the sensitivity analysis of how to perform sensitivity analysis in LP and also about the dual theory. But that's something that will come after this week. Okay, so the learning objectives is use the simplex algorithm to solve linear programming models involving equal and or greater or equal constraints. So far, we have been using the simplex algorithm to solve problems that have only less than or equal constraints. And when that happens, you only add a slack variable, you make those constraints equalities, and then you can apply easily the simplex method. But what happened is that will not work when you have constraints that are already equalities and when you have constraints that are greater or equal. And you will see why that is the case. Okay, so for those cases, we're gonna use two methods. The first one is called the M method, and the second one is called the two-phase method. And here I'm highlighting those sections in your textbook that cover that material. Okay? So the agenda, again, we're going to start talking about artificial starting solutions. Then we're going to discuss the two methods, the M method and the two-phase method. So let's talk about the artificial starting solution. So first, actually 4 weeks, we've been covering this material, how to model linear programs, how to solve two-variable LPs using the graphical method, and we also covered the simplex method. And that was part of our first exam. Now we're going to extend what we already know about the simplex method. So, however, LPs in which all the constraints are less than or equal with a non-negative right-hand side offer a convenient all-slack starting basic fixable solution. So when you saw that, you want to change your program to the format for the simplex method. You add those slack variables and you perform and you create those equalities. But that's not always the case. So models involving equalities and greater or equal constraints do not have that flexibility. You cannot add those slack variables and start constructing your simplex method. So for those cases, the procedure for starting the LP with equalities and greater or equal constraints is to use artificial variables that play the role of slacks at the first iteration. So instead of, well, we're going to add our slack variables when needed. We're going to add also the additional slack for the greater or equal constraints, but we also going to add the artificial variables for our program. So the artificial variables are then disposed of at a later iteration. So you'll see we're going to start with those artificial variables, but then when we get our first initial solution, we're going to discard those variables and we're going to continue the Simplex method. So two closely related methods are introduced in this lecture. Again, the M method and the two-phase method. Okay, so I'm going to start with this one. And I believe it's easier to understand, so we're going to start with the M method. Then we're going to transition to the two-phase. So the M method. So the M method starts with the LP in equation 4. If an equation I does not have a slack, an artificial variable Ri, so we're going to call our artificial variables with a capital R, is added to form a starting solution, similar to the all slack variable solution. The artificial variables are not part of the original problem. It is a modeling trick that is needed to force them to 0 by the time the optimal iteration is needed. So we're going to start our method using these artificial variables, but by the time that we get to the optimal tableau, we're going to force those variables to 0. So they are not part of the problem anymore. Okay, so we add them and we then force them to be outside the problem in order to get the optimal solution. Okay, so the desired goal is to achieved by penalizing these variables in the objective function using the following rule. So we're going to use a penalty rule for the artificial variable. So given m, and n, capital M is going to represent a large number, and it is a sufficient large positive value, so mathematically that m can go to infinite. The objective coefficient of an artificial variable represents an appropriate penalty if the artificial variable objective coefficient is minus m in maximization problems and positive m in minimization problems. And you'll see how that applies to our method. Okay, so we're going to use this large number. We're going to put that large number as a coefficient of our artificial variable, and that will force that artificial variable to be 0 by the optimal tableau. Okay, so those are the general ideas. Now we're going to work with them, and then you will see how those apply to a practical problem. So let's start with this problem. And this is a problem you have seen before, I believe, in one of the homeworks. So we're going to start with this problem. This is a two-variable problem, minimization problem. And you see that we have different constraints. One is inequality. This one is a greater or equal constraint. And this one is a less than or equal constraint. So we can, using EI as a surplus in the second constraint and S1 as a slack in the third constraint, the equation form of the problem is given as this. Okay, so we change the first constraint is already an equality. So we don't have to do anything with that one. Okay, remember what we're trying to do is to apply the simplex method. Okay, so in order to apply the simplex method, you need to change all the constraints to an equality form. So, but this case is different because we have different type of constraints. First one is inequality. So in that one, you don't have to add a slack or a surplus. So that one remains the same. For this one, in order to make an inequality, since this is a greater or equal constraint, you need to add a surplus. Okay, so you subtract that surplus. And then the last one is typical for the one that we have seen in class about. So you add a slack variable to make it an equality. And all those variables need to be greater or equal to 0. Okay, so that's something that we have done in class already. So we are just applying that knowledge to this problem. Now, this is how the problem looks like right now. So I want you to help me fill out this table. So what I'm doing is, this is the typical tableau, the initial tableau. I'm putting here a column, or basically adding a new name for that column. I'm going to call this column the basic variables. And then the first row is basically the row representing the objective function. And the other three rows are the rows for the constraints. So let's fill this table. So for row 0, what would be the value of x1? -4, correct? And for x2? -1, correct. So with our options, so we have -4, -1, and then 0 and 0. Okay, so for the sake of, for the first constraint, we have 3, 1, 0, 0, and the right hand side is 3. We also have, for the second constraint, we have 4, 3, -1, 0, 6. And for the third constraint, we have 1, 2, 0, 1, and 4. Okay, so that's our initial tableau. Okay, so how many from the tableau you can identify how many variables or basic variables do we have? Two. Why 2? No. So you can identify the basic variables by looking at the columns, but it has to be a positive one. So right now, you only have one basic variable, which is S1. Okay? So we only have one, and that basic variable is S1. Now, how many basic variables do we need in order to solve this problem? And this is going back to one of our first lectures, in which we were, based on the number of constraints and the number of variables, you can identify or you can compute how many basic variables you need. And our conclusion in that lecture was that you need n number of basic variables, where m is equal to the number of constraints. So for this problem, we need 3 basic variables. Okay, so by now we only have 1, but we need 3. So the way the tableau is right now, it's impossible for us to find an initial solution because we only have 1 basic variable and we need 3. Okay, so can you easily obtain the basic variable needed from this tableau? Well, one thing that you might consider is multiply this row times -1. So what will happen is you will have a positive number here, but this number, the right hand side, will be negative. And that cannot happen. So you cannot easily obtain the basic variables needed from the tableau. So does it work to multiply row 3 by -1 to make x3 basic? Yes or no? Everybody told you the solution, the answer. No, it will not work. Multiplying the third row by -1 problem turns infeasible because you have a negative right hand side. Okay? And in our previous lectures, we easily found our basic variables because you were adding slack variables, all of them were positive, and those slack variables were giving you the basic variables that you needed for the initial solution, or the initial feasible solution. But right now we don't have those slack variables in all our constraints. We only have a slack variable here, but these two constraints, they do not have a slack variable. Okay, so what we're going to do now is we're going to find an initial solution by using artificial variables. So adding artificial variables, when an initial basic feasible solution does not exist, an artificial variable Ri greater or equal to 0 can be added to the constraint, and it will guarantee a starting basic solution. Excuse me. So artificial variables are added only to the constraints with equalities or greater or equal constraints. And you see why we don't need to add those artificial variables to those constraints that we already have the slack variable, because you already have a one positive, and that can be part of your basic initial solution, or initial basic feasible solution. But if you have a negative number, that would not be part of your initial solution. So that's why we need to add those artificial variables to our constraints. Can I go to the next slide? Okay. So the third equation of this problem has its slack variable x1, but the first and second equations do not. Thus we add the artificial variables r1 and r2 in the first two equations and penalize them in the objective function, adding that big M times each artificial variable in the objective function. So the resulting LP is given as follows. So we are adding our artificial variables here. These two are our artificial variables, so we are adding them to the first and second constraints. Okay, so now we have this equality with an artificial variable, which is different to the one you're going to add to the second constraint. This second constraint still have this surplus E1, but it also has the artificial variable. So you're going to have both in the same constraint. And that, remember, that constraint was a greater or equal constraint. For the last one, or third constraint, you keep your slack variable and you don't need to add any artificial variable. Okay, so what we did was we added those artificial variables to the constraint that they have a basic contribution to the initial solution. We added those artificial variables, right? And we also penalizing those artificial variables here in the objective function by adding those artificial variables with an m value. This m value is a large, very large number. So what will happen is, let's say this m is 1,000. If that m is 1,000 and this one is 10,000, and you're trying to minimize your problem or your objective function, what do you think the problem is going to try to do? If you want to minimize the summation of this. If those coefficients are that big, what you're trying to do, or what the problem is going to try to do, is to make these artificial variables 0, or the minimum value they can be. Because if this is 0, they will not contribute, and the value of the objective function is going to be very small. But if this is 1, for example, then you are already adding 1,000 to your objective function. So the idea is to add those artificial variables to start solving the problems, but at the end, you want to penalize them with a big number because you want them to be 0 at the optimal solution, because those are artificial, those are not real variables. The only thing that we are doing with them is just starting to solve the problem. But at the end, we don't want them to be part of the solution. We want them to be 0. So the only way that you can make them 0 is to penalize them with a big number in the objective function. Okay? So that's the general idea. You add those artificial variables, you want to get an initial solution. Once you get the initial solution, you know that by the end of the solution, those variables that are artificial are going to be 0. Because if they are not 0, you're going to have a big objective function if you are minimizing. Okay? So now we have the starting basic solution, because this will have a coefficient of 1, this one will have a coefficient of 1, and this one will have a coefficient of 1. Those three are the 3 variables that we need for our basic solution, or initial basic solution. Okay, so R1, R2, and S1 equal to 3, 6, and 4 is our starting basic solution. Okay, so from a computational standpoint, solving the problem on the computer requires replacing n with a sufficiently large numeric value, which is sometimes it's not that easy to find. In this particular problem, and in the class, in this course, we're going to use the coefficients of the objective function to maybe try to guess a sufficient large value that can be used for the problem. So, for instance, what value of the m should be used for this problem? The answer depends on the data of the original LP, but the penalty must be sufficiently large relative to the original objective coefficients to force the artificial variables to 0 in the optimal solution. Okay, so the penalty must be large or sufficiently large relative to the original coefficients to force the artificial variables to 0 in the optimal solution. So this m has to be large enough when compared to the coefficients of x1 and x2. Let's put that back. So in the present example, the objective coefficient of x1 and x2 are 4 and 1. So it appears reasonable to us to set m equals to 100. Because when you compare 100 versus 4 and 1, that number is large enough. But you can use 1,000 if you want, 10,000, but it has to be a major difference between those coefficients in the objective function and the m value. Okay? Because that's what's going to force the problem to make those artificial variables 0. Okay. So knowing that, we can go back to the problem and let's fill this table. So now we have a new set of variables. Those artificial R1 and R2. We'll still have our slack, so we can construct an initial basic solution from this problem. Okay, so which ones are from here? Okay, so we said that m is going to be equal to 100, right? So this and this are 100. And using that information, we're going to complete the table. So for x1, z will be equal to -4, -1, 0, minus 100, and minus 100 and 0. Do you understand why we're putting here a minus 100? Remember, we need to move all these coefficients to the left side, and that will make the coefficients negative. So this is C, this is C, this is not a 2, this is Z, the objective function. So minus 4, minus 1, no values for the surplus, minus 100 for the coefficient of R1, minus 100 for the coefficient of R2, and no slack variables in the objective function. Okay, so now we can go to the first constraint. Questions? Okay, so we change the value of m to 100. Again, that m value has to be sufficiently large when compared to the other two coefficients. It could be 200, 300. The important is that the number has to be large enough. So you can force those two artificial variables to 0 in their optimal solution. So now let's work with the first constraint. So the coefficient for x1, this is our first constraint, is 3, 1, and we have 1 for R1, and the right hand side is 3. Then our second constraint, so this is the first one, second, third. So the second constraint is 4, 3, minus 1, 0, 1, 0, and 6. And the third constraint is 1, 2, 0, 0, 0, 1, and 4. So for the last or the third constraint, we don't have a surplus, we don't have an artificial variable, we only have the slack. Okay, so I want you to tell me which are the three basic variables in this tableau. So the first basic variable looks like this one. We have a minus 100 here. Same problem with this one. This one is a basic variable. So let me list those here for now. So the purpose of adding these artificial variables is to make them basic variables in our initial solution. So let me list them here: R1, R2, and S1. But we know that for them to be basic variables, these two numbers need to be 0. So we need to change that. Okay, so before, this is the same tableau. We still have those numbers here, and we have R1, R2, S1. We want to make these two basic variables. So before proceeding with the simplex method computation, the 0 must be made consistent with the rest of the tableau. And when I say that is, we have to make these two numbers 0. So the right hand side of the 0 in the tableau currently shows 0, z equals 0. However, given the no basic solutions, x1, x2, x3 equals 0, and the current basic solution, R1 equals 3, R2 equals 6, and S1 equals 4. These values are coming from here, so R1 equals 3, R2 equals 6, S1 equals 4. That will yield a objective function value of 900. To eliminate the inconsistency, we need to substitute out R1 and R2 in the 0 using the following row operation. So we're going to use our row operations to make these values 0. Okay? So this is the operation that we need to do in order to make those two equal to 0. So we go to the next slide. Still have the same tableau. So we want to make these two 0. So what do? You multiply this row times the 100, and then add that to the 0 row. So if you do that, you will get, and actually you do that for the first row, and then you do that for the second row as well. So you're going to multiply this one by 100 and also add that to here. So when you do those two operations, so again, you want to make this 0. So you multiply this by 100 and add here, that will become 0. You multiply this row by 100 and add to this row, that will be 0 as well. So when you perform those operations, this is how the first row values will be. Make this more clear. Okay, so first 100 times row 2 plus row 0, and then 100 times row 1 plus row 0. That will give you this 0 row. Okay, so now we have the tableau in the format that we need to apply the simplex method. So it took a while to get to this point, but this is the tableau we need in order to apply what we already know, which is the simplex algorithm. Okay, so we started with a tableau with no basic solutions, so basic variables. We added our artificial variables in order to make them part of the basic solution. But what happened is when you add those artificial values, you still have to modify your row 0 because those numbers are not 0. So in order to make them 0, we perform our row operations, and that will give us this new tableau. And using this tableau, we can apply the simplex method because we have our basic variables. We have the format we need for those basic variables. So we have R1, which is an artificial variable, equals 3, R2 equals 6, and X1, our slack variable, equals 4. Okay? So what will be the next part? The next thing is to look at which variable will leave the tableau and which variable is going to enter the tableau. Okay, so for that we know that we need to apply the ratio for the tableau, but we need to identify first which is the variable that is going to enter. So this is a maximization problem, right? So what will be the variable that enters the solution? It's a minimization problem, right? So we want to add the largest positive value, right? So that one is X1. And if we perform the ratio, this will be 3 divided by 3, so this is 1. So we are looking at this and this. This one will be 6 divided by 4, which is 3/2. And we have 4 divided by 1, so this is 4. So based on this guy will leave the solution, and x1 is going to enter the solution. Okay, so the result is that R1 and R2 are now substituted out as zero coefficients in the Z row, with Z equals 900 as desired, right here. The last tableau is ready for the application of the simplex optimality and feasibility conditions. The variable x1 having the most positive coefficient in the Z row enters the solution, and that's what we identify here. And the minimum ratio of the feasibility condition specifies that R1 is our leading variable. And that's what we saw by looking at the ratios. Okay, so what's next? What do we do next? It's something you already know. We need to pivot this number. So we need to make that one 1. And the other coefficients in this column 0. So this should become 0, this one 0, and this one 0. And then perform another iteration, check if you have another positive value, enter new variable, look at the variable that needs to leave, check if you have another positive, and continue. So you know the process already. The only thing that you needed to understand is what will happen if you don't have an initial solution. So this is what you do. From here, you know what to do next. It's just performing the simplex algorithm steps. So once entering and the living variables have been determined, the new tableau can be computed by using the familiar Gauss-Jordan operations. So this is what's going to happen. You're going to perform the Gauss-Jordan operation. You're going to make this 1 and this coefficient 0. Look at the tableau. Now you have x1 entering the basic. You still have a second artificial variable in the tableau. So this is not the optimal tableau. Can you see why? Why is that not optimal? There's some minimization problem. Right. So you still have a positive coefficient here, so that variable can enter the solution. So you can perform another iteration. So continuing with the simplex computation, 2 more iterations are needed to reach the optimum, and the optimal value will be this. So you can compute that on your own if you want to, but again, this is straightforward from what you already know. The important part of the lecture for today is just understanding how to get that initial tableau when you don't have a less than or equal constraint. Okay? So from this tableau up to the optimal solution is just the same thing, applying the simplex method. Okay. So that covers the first method, which is the M method. Any questions? I'll provide you with some homework problems just to see if you understand it. But again, the idea is, if you see this type of problem, something like this, where is it? This, we should have equalities and greater and equal constraints. You still can apply the simplex, but you have to use one of these methods, the M method, to find an initial solution, or the second method that I'm going to explain now. Okay, so that only applies when you have these type of problems, greater or equal, equality, and so on. Okay, so let's look at the second method. And again, this is a different method, but the objective is the same. You don't have the nice looking or the nice type of problem to apply to simplex. So you need to find a way to find a new or initial solution. Okay, so the two-phase method eliminates the use of the constant m. So we're not gonna need that m value for the coefficients of our artificial variables. But the method solves the LP in two phases, like the name says. Phase 1 attempts to find a starting basic feasible solution, and if one is found, then phase 2 is invoked to solve the original problem. Okay, so I took these descriptions from your textbook, and it's a description more in detail what I just said. So phase 1, put the problem in the equation form and add the necessary artificial variables to the constraints, exactly as the method, to secure the starting basic solution. Next, find a basic solution of the resulting equation that always minimizes the sum of the artificial variables, regardless of whether the LP is maximization or minimization. If the minimum value of the sum is positive, the LP problem has no feasible solution. Otherwise, proceed to phase 2. So this is very important. So if you solve the first or the phase 1 of the problem, if the minimum value of the sum is positive, the LP problem has no feasible solution. Okay, so that minimum value has to be 0 or negative. So if that is the case, if you find a 0 or a negative value, then you can proceed to the second phase. On the second phase, use the feasible solution from phase 1, the starting basic feasible solution, to the original problem, and proceed as the simplex method. Okay, so let's look at the same example. We start with three types of constraints: equalities, greater or equal, less than or equal. So we add our surplus slash variables. We have all of them in equality form. In phase 1, the attempt is to find the starting basic feasible solution for the original problem. So that's all we're going to do in the first phase. We replace the objective function z, regardless of minimizing or maximizing, with minimizing r. R equals the sum of the artificial variables, and solving this new minimization problem. So this is how the objective function is going to look like. We're going to sum the artificial variables that we have. So if we have only one, there's no summation, it's just the single artificial variable. But if we have two artificial variables, then we need to add them, and we're going to minimize the summation of the two. And that's what we're going to do in the example. So instead of using the original objective function, we're going to discard that objective function in our first phase, and we're going to substitute that objective function with the summation of the artificial variables. So let's see how that applies to this problem. So remember, this was our objective function, but now we're not using that objective function. In our first phase, we're just going to minimize the summation of the artificial variables that we added to the problem. Okay, so we still have our constraints, but the objective function is to minimize these artificial variables. So the starting basic solution, again, is R1, R2, and X1 with this value. So again, we can use that problem or that formulation for the first phase to establish our initial tableau. But again, we have the same problem. If we look at the objective function, now we have a -1 in R1 and -1 in R2. We can say that we have our artificial variables as basic, but we still have to change these values to 0, as we did for the M method. So we are able to find our basic variable solution, but we'll still have to perform one more step, which is changing these numbers to 0. So before proceeding with the simplex method computations, the R row must be made consistent with the rest of the tableau. So R1 and R2 are substituted out in the R row by using the following row operation. So we're going to perform those same steps to make those to make that row 0 in the tableau. So I think I have that in the next slide. Okay, so we are going from here to here. So again, we need to perform 2 row operations. The first one is row, so let me make this 0, 1, 2, and 3. So row 2 times 1 plus row, this is row 1, sorry, this is 1 plus row 0, and the second operation is row 2 times 1 plus row 0, and that will create this new row 0. So if you see from this row down and this one, the only difference is this row 0. And the reason we need to perform this operation is to make these two values 0. So as you can see now, these are 0. We have a new right hand side, and we have new coefficients for x1, x2, and e1. But we found our initial basic solution for phase 1. So we have R1 equals 3, R2 equals 6, and X1 equals 4. Okay, so we are doing a minimization problem. So we are not done yet, because as you see, these two numbers are positive. So that means you can insert that X1, in this case, to the basic solution, and take out this R1 from your basic solution. So if you go to the next slide, you will see the operations that we need to perform in order to get the optimal solution for the phase 1 of the two-phase method. So we find our pivot here for the first iteration is this one. So this guy is going to enter X1. R2 is going to leave the basic solution. We perform the operations. We get this tableau. We still get a positive number here, so this X2 can enter the tableau. You look at the ratio here, the minimum for the ratio is R2, so that means you're going to pivot X2 in this row 2. So you have to make this 1 and the other coefficient 0. So when you perform that iteration, this is the final tableau for phase 1. So as you can see, the right-hand side for the first tableau, the objective function, is 0. So that satisfies the condition that the objective function needs to be not positive, so 0 or negative. So this one is 0, so we can transition to the second phase. So as you can see, this phase 2 method takes a lot of steps because you have to implement or you have to perform the simplex method to get the optimal solution for phase 1. So this is what we have done so far. We got the optimal solution for phase 1, and that is x1 equals 3 over 5, x2 equals 6 over 5, and x1 equals 1. Okay, so the new R row is used to solve for phase 1 of the problem. We use the optimal tableau. So this is the optimal, it's the same tableau from here. Okay, so because R equals 0, phase 1 produces the basic feasible solution. X1 equals 3, 5, x2 equals 6, 5, and x1 equals 1. This is coming straight from the tableau. So at this point, the artificial variables have completed their mission, and we can eliminate their columns altogether from the tableau and move on to phase 2. So what we're going to do is you're going to delete these 2 columns, and we're going to continue our solution in phase 2. Okay, so phase 2 is going to start with this problem. And this is coming from here. So if you delete this, and you write this tableau in equation form, you will have from the first constraint is x1 this one is x2, it's positive, this is minus 3, and that is here. So we are using this optimal tableau from the phase 1 to build the initial solution for phase 2. So the problem is going to use the coefficients, delete these 2 columns, use the coefficients and build the new constraint for phase 2. Here they are. And we now use the objective function of the original problem. Okay, so phase 1 help us to find the initial solution, and we use those coefficients to build a new problem for phase 2. Phase 1 has transformed the original constraints, equations, in a manner that provides a starting basic feasible solution for the problem. Okay, so from here, what's next is just applying the simplex method. So you can build a new tableau from here. It's just using the coefficients from the problem. This is an initialization problem. So again, when you do that, what's going on? So your basic variables are x1, x2, and x1. But when you look at the row 0 of the tableau, you have some coefficients that are not 0. So you need to make those 0. And that will be the same thing that we did for phase 1. So we need to make those equal to 0 because those are your basic variables. So again, because the basic variable x1 and x2 have no 0 coefficients in row Z, they must be substituted out using the following operation, which is again multiplying this row times 4 in this case and adding here, and multiplying this by 1 and adding to row 0. And that is right here. That's what we are doing to make those coefficients 0. And once we perform those operations, this is how the tableau is going to look like. So now we make those 0. Our basic variables are in good shape now, but we'll still have one positive number here. It's a minimization problem. So this variable can enter the solution. The application of the simplex method will produce the optimal in one iteration. So the removal of the artificial variables and their columns at the end of phase. So I don't have the actual solution for the problem. I think it's a tableau. But if you perform one more iteration, you will see that the optimal solution is just the same that we found for the M method. Okay? So after one iteration, you will find the optimal solution. But again, it's just applying the simplex method to this tableau. Okay, so to summarize, the removal of the artificial variables and their columns at the end of phase 1 can take place only when they are all non-basic. If one or more artificial variables are basic at 0 level, then the removal requires the following additional steps. Select a 0 artificial variable to leave the basic solution and designate its row as the pivot row. The entering variable can be any non-basic variable with a non-zero positive or negative coefficient in the pivot row, and perform the associated simplex iteration. And step 2, remove the column of the just leaving artificial variable from tableau. If all the 0 artificial variables have been removed, go to phase 2, otherwise go back to step 1. So this is another case that can happen in the two-phase method, and we're going to cover one problem in which you're going to see this problem next time in the class, okay, in the classroom. So just keep in mind that there's some cases that will not be that straightforward. So we're going to go over another example on Tuesday. Okay, so my recommendation at this point, I'm going to assign a homework today, but it's going to be due in a week. So you're going to have to turn it in on Thursday. We're going to go over these methods one more time on Tuesday. So just to give you time to understand it a little bit more, maybe go through the slides one more time before Tuesday. You're going to practice that problem on Tuesday, and then if you have more questions for the homework, you can ask them during the class period. But for now, again, these are the two methods that you can use to solve problems when you don't have all the constraints being less than or equal to. Okay, so any questions at this point? Okay, so again, we're going to discuss another problem on Tuesday. You can go over the slides one more time. That would be great. But now what I want to do is to pass the exams and discuss the exam. Okay, so